everyone. Welcome to MORS 2022. This is the second year that we are organizing multi-objective recommender systems workshop. Last year it was online, and this year I'm very excited to see many of you in person. For the authors, this is very important because we don't want to have some online problems with the organization. Please email your slides to this email address to my colleague Zahra Nazari, such that we can use the same laptop for every presentation. So please email your slides there. So this workshop is a joint effort between many people, including myself. My name is Himan, and I'm very excited that I have been able to kind of work with these amazing people. Sherry Sahibi from sunny USA, Mehdi Elahi from University of Bergen, Masoud Mansouri from University of Amsterdam, Babak Loni, he was ING Group, now he works at Meta, Zahra Nazari, and Maria Dimakopoulo, both from Spotify. Thanks so much for this great work, and hopefully we can do this again in other years. And also I would like to give a special thanks to the program committee members of MORS 2022. They were really great, and they had amazing reviews for the papers that they were submitted in such a short time, probably in less than 2 weeks. We received such amazing reviews, and thanks so much for all of you for the work that you have done. MORS 2022 is going to be a half-day workshop. So we will be here until I think until 12:30. So it's a half-day workshop. We received really great papers. We received many papers we didn't expect. We will receive so many, but they were amazing papers, and because it was only a half-day workshop, we couldn't accept many of them. But we were able to accept really great papers this year, which you will see during the workshop. The workshop starts with a keynote speaker by Professor Diet Mariana on multi-objective recommendation overview and challenges. And then we will have 2 papers for the first session. Then we will have a break. And then after the break, we will have another session with many other amazing papers. And in the end, we will have a poster session. Initially, we thought the posters will be in the room, and that's why we had a separate poster session, but it seems they are just in the common area. So probably during the coffee break, you could still have some poster sessions, which that would be great. And now I am really happy and excited to introduce our keynote speaker, Professor Diet Mariana. He sent me a very humble bio, which I don't think it does a fair job of introducing him, but I'm just going to read his bio. Professor Diet Mariana is a professor of computer science at the University of Klagenfurt, Austria. His main research theme is related to the application of intelligence system technology to practical problems and the development of methods for building knowledge-intensive software applications. In recent years, he worked on various topics in the area of recommender systems. In this area, he also published the first international textbook on the topic. I would add that he is definitely one of the main leaders in the RecSys community, has a lot of very influential papers in this area. So I'm personally very excited to hear his presentation. Please.
Yeah, thank you very much for the kind words and the introduction. Would we put this over here? Yes, welcome everybody. So I'll take the opportunity at this keynote to talk about, I try to create a short first overview on the topic based on literature I found. And so I hope it's a first step to better understand what's going on in that field. And again, thank you for the invitation. Unfortunately, I have to leave directly after the Q&A to catch me up. So apologies for that. The slides can be found online. Later on, I'll show that again. It's tinyurl.com, MORS2022 slides, and there's a small extended abstract which you can also find there, which should be in the proceedings soon, which mainly covers this this presentation of today. So talking about objectives, this has to do with goals and purposes, and I tried to come up with an alternative definition of what the recommender systems is for in terms of objectives. So I came up with like recommender systems are software solutions, that's clear, to provide users with convenient access to relevant content. And this definition is designed to be very generic to cover a variety of purposes for which we build such systems. And the convenience that is mentioned here can be manifest itself in different ways, like usually guide users to relevant items in situations of information overload, help users discover new things, that's all the convenience. Just reminding people of things that they liked in the past or want to listen to again or watch again. It can also be done through a recommender system. And such a system can also, the convenience can be that the system just plays the next tracks on your favorite streaming service. Is it okay?
Position of the camera, I think.
Oh.
That's right.
Oh, thank you. So there are various purposes, various objectives that the system can be helpful for. So that the most common one, or at least implicit objective, not all this is mentioned in the papers, is that the recommender system is there to guide users to relevant contents in situations of information overload. And this is implemented usually through ranking or filtering a large set of items according to user preference. And then if you go from that definition to operationalization, how do we do research here? We often see recommendations just as a supervised machine learning problem. And the task often is like just learn parameters of a complex function or network from noisy data. And what we do is we predict the relevance. That's the purpose more or less. And then we rank or filter the list based on these relevance predictions. Now I can't move on. I need help. Oh no, sorry, here's skip one, yeah. Okay, so we're talking about, okay, what's the purpose? How do we do research here? So we learn a function, and the goal here, if you operationalize the task of the software, is you create a length restricted recommendation list, like the top N list, and having usually the most relevant items on top. And then we quantify if we achieve the goal or the objective of our research by using various accuracy measures, using usually database experience, historical data sets. But we could also do, and there are some works that try to monitor user perceptions or assess user perceptions in user studies, or even in field tests, in an A/B test, to see how people react to your recommendations, if they consider them relevant or want to explore them. So this is the primary way we do it. And this has like a historical note. We do this for a long time. And this is 1994, is a landmark system, the group lens system. So it's almost 30 years. And roots go further back to even to the 1960s. And this is a very common research operationalization. So we use collaborative filtering. We have the assumption we have this matrix of users and items and who rated what. And the goal at that time is to predict the empty places in the rating matrix. And at that time, the method here, when the groupless system was developed, is they suggested to use a nearest neighbor method, just look for similar users and take their preferences, predictors for the current user. An interesting part here maybe is, and these are screen captures from the papers from 1994. So at that time, they were building systems. So it's not building just a network model or some algorithm, but they really try to develop a system. So here you see the interface where you can rate different things, and then you got a recommendation of the news that come in, and these were filtered. And so it's really a bit beyond what we do here often. And measurements, I think, I'm not sure in the groupless paper they had a measurement or experimental evaluation. They just proposed this architecture for filtering. But what in the 90s already, this is one paper I found from 1995 that uses the mean absolute error as a prediction measure, or to measure again how if we achieve the objective, and says, okay, the mean absolute error must be minimized. And you see commonly used metrics today. RMSE is not so popular, but ranking metrics of all forms. These are the objectives we seek to optimize more or less in the majority of papers. Going back, and this is another screen capture from that paper from 1995. On the right-hand side, you see the rating scale. So it's again looking at the user interface, and it's about the system. And they were very creative in inventing a nice rating scale for a music recommender system. So, so we can say, like, if we talk about objectives, single objective, maybe here we're working on prediction or ranking optimization since almost 30 years now. Yeah? Hundreds, thousands of papers every year, improving the state of the art. There was an interesting keynote yesterday by Kim Falk about the state of the art, if it exists, or what it is. And apparently, since we have many papers here, the problem is not solved. So we're still having every year 5% per paper improvement. So probably we're already there soon. And the assumption of all this research mainly is that when we optimize the accuracy measure, which is our main objective, this leads to a better system. That's the underlying assumption. And that's, it might be a useful assumption, but maybe it's not complete in some ways. So, and if we go back to the definition, saying, okay, we want convenient access to relevant content, well, what's relevance, right? And this is the example. I don't know who came up with this first on all its optimization. So let's assume the user like these 3 Star Wars movies, and that's what the system recommends is another 3 Star Wars movies. And now you can say this is relevant. So it's the Star Wars lover. These 3 recommendations are relevant, but is there any value? And here, if you recommend these 3 movies, MAE will also be close to 0. There's 0 error. You predict 5 stars, and there will be 5 stars. It's really optimal recommendation. But on the other hand, it's no value probably for the consumer or the provider because the consumer would say it's boring, I found nothing new, I know these things already. And for the provider, it could even have a negative impact, like because the user would have watched or purchased them anyway, and you could have used the screen space there to promote something else, right? So it's a missed opportunity also, right? So, and this is nothing new. So I really want to put this a bit into perspective of history. Like 20 years ago, there were papers saying, okay, it should be more diverse, like here from Barrett Smith and colleagues, a number of papers on improving recommendation diversity, the highly invisible paper from the group lens group, being accurate is not enough, and they say even accuracy metrics hurt recommender systems. This was 21 years ago. And what do we do today? This is a bit provocative, like it's accuracy optimization. Still, the main thing, if you look at the papers, maybe here at other events, is that, and I don't know if you know the Twitter account, Neuronet guesses memes. So it's like typical failures of recognizing, categorizing a picture. And this would be like image prediction. We see people in a room, right? 100%, nothing else to see here. And I think people know for 20 years, this is a bit a strong assumption that we built on here. And also we had a paper on, was involved in a paper at UMAP. We tried to benchmark recent algorithms in a reproducible way with very small data sets, but these data sets are representative of what we had 20 years ago, like movie lens 1M plus filtering. And there's some ranking of algorithms in the multitude of measures, but you see user KNN is in place 4 on many of these rankings. So after 20, 30 years of introducing user KNN, we of course, we see it progress, but it's not like it's, yeah, justifying thousands of papers maybe. But this is, you know, this is a bit provocative, right? So what we should do, and this is preaching to the choir here in multi-objective workshop. So we have the single objective, and being able to predict the relevance of items will remain important. I think that's still an important feature of any algorithm or any system. That underneath, one part is about having accurate predictions. However, optimizing only for one objective or metrics may be too simplistic, because we know there's a lot of different purposes, which we already discussed, including discovery, entertainment, information filtering. And there's a number of different ways these systems create value for consumers, like engaging users, serving long-term retention, and these things like that, more from the business perspective. So this is where we should go. And we also try to develop some position paper with Christine Bauer about escaping the McNamara fallacy in recommender systems research, because the danger is if we continue optimizing for accuracy, we optimize for something that we can easily measure. And this guy McNamara was a Minister of Defense in the Vietnam War of the US, and they were using, I think, body counts of the enemy, how many they killed, as an indicator of progress of war, which turned out to be not the best metric in some ways. So they measured something that they could easily measure. And I think in our field, we do too much of things that we can easily measure. And in this paper about how to escape this fallacy, one part was like we should look at multiple objectives in parallel, like many works in this workshop do so. So that's very good. When you look at multiple objectives, we can have situations where these are aligned, like higher diversity in the recommendations may lead to more engagement, and maybe you resubscribe on your favorite music service, Spotify or others, right? In other cases, and this might be competing, because if you provide more diversity, you will help the user explore new stuff. It's more risky, and then maybe the accuracy or relevance would go down. And often in works we see on multi-objective optimization here, it's often about to balance these different goals in some way. And with some side remark, often what the right balance is assumed to be given, which is another strong assumption here. So in the context of this presentation, I tried to figure out what kind of different dimensions we have. So we have, first of all, these three dimensions I identified to have competing quality objectives, like diversity increasing without sacrificing relevance or accuracy. You might have competing stakeholders. It's another dimensions, like consumer versus provider. So, or increase profitability while maintaining consumer satisfaction. Or you might have also types of goals that are different in terms of the time horizon or temporal objectives, like do you optimize for short-term clicks or for long-term engagement? So this might be different things to look at. And I'll walk through the first one because that's the most common one in our field. So I try to differentiate between the individual level competing objectives and aggregate level things. So one example of research, I think, that falls into the multi-objective domain, even though it's not framed as that, is that people have multiple decision criteria. So you look for a restaurant, you by your own one consumer alone has various quality goals or objectives to fulfill, like a certain type of restaurant, the distance, the price category, and so on. And the recommender system should try to balance these competing consumer requirements. So this can be framed as a multi-criteria decision problems, and there are a number of papers that do that. In these cases, in some of these works, it might really be helpful when you show the recommendations that you explain to the user, because some of the criteria are not fulfilled to a good extent. So you should explain to the user why you came up with these lists. So again, this goes beyond just the algorithmic perspective. You have to do something on the user interface. And there's also some works, also I was involved. What happens if the user has a lot of criteria, but you have no recommendation left? So usually what you do, you always recommend something. Right, a good salesperson would always have something. So what you try is you relax some of the constraints automatically, maybe, and then again there are algorithms to find an optimal relaxation of the constraints, which you again have to communicate to the consumer, because user will notice if this is a different type of restaurant or a bit a pricier one. Another type of competing objectives, it's I put in this category of individual level, is called calibration. It stands the question if there's a better categorization, but the idea here is that you create a recommendation list, which is not only containing relevant items, but you try to match other quality criteria. For example, for diversity, the first work I found on this is from 2011, and they try to match the popularity tendencies of a user. So if the user only like mainstream, more mainstream. So you take the accuracy optimized list and then you adapt it to match the popularity level of the user. Technically, often this is done by minimizing distributions, like distribution of diversity of genres, for example, in the music domain. This is also related to next track music, and we did a bit of work here that we have, like you have a playlist, user listen to 5 tracks, you have a continuation. You don't not only want to have the most accurate ones, but those that match, let's say, the tempo of the preceding tracks here. And this can be technically done often with re-ranking. You get an accuracy optimized list and then you re-rank. More common and earlier, looking at these papers from 2001 and onwards about diversity and other beyond accuracy measures, we have a lot of these beyond accuracy measures, many of them covered in the conference here: diversity, novelty, serendipity. So I talked yesterday. Popularity bias is important. Heman did a lot of work on this. Catalog coverage, or most recently also fairness, which is another very difficult problem. And usually, in many cases, the objective is increase one of the other objectives while not sacrificing accuracy too much. So that's the framework here, more or less. There are cases where this balancing is not always a contrast and the objectives are in some ways synergistic. So we had one work on music recommendation I just mentioned. So we had the playlist that the user listened to, we made continuations and then tried to make it coherent in terms of tempo and things like that, or energy. And then we re-ranked the list and got even better accuracy in some cases. So it didn't, at least it didn't get worse in offline experiments. So, but in most cases, I think it's a compromise. There are also in the literature a number of variations. Sometimes you have accuracy versus one another dimension, and sometimes you have accuracy combined with a multitude of other measures. In music could be coherence, tempo, genre distributions, whatever you want to achieve in the continuations. And there are other different ways you implement that, or the problem settings can be different. Sometimes you have a given threshold or a target distribution, like for popularity or sometimes fairness, which we have to discuss still. You want to match individual user preferences, which corresponds to the calibration approach. Sometimes when you do, you design a new algorithm, you might just say, okay, I have a new algorithm which is competitive in terms of accuracy, but has better diversity. That's also a way you want to frame this research. And most typically, you want to limit the loss in accuracy. You may say, okay, I increase the diversity metric by 10%, while only giving up 2% of accuracy in whatever measure you use. Then there's also a whole stream of research on all these explore-exploit problems, usually from reinforcement learning. So the question here is, do you want to make safe recommendations, continue to do that, or do you do something more risky and explore something? And like also again in the music domain, the example is here, you try and help the user to discover something. So you always recommend, if you always recommend what the user likes anyway, the user will maybe quit the service at some stage if they don't find anything new here. So this is a good example here, and often we see a whole stream of research on these reinforcement learning approaches. Looking at the technical implementations, like I just tried to identify the main families. So often you have like re-ranking and accuracy optimized list. This is the nice thing, you can do that with any method you have underneath, complex or simple. It's simple, fast, and effective. You can do a greedy re-ranking really in real time, and the greedy methods will not find the optimum, but often they're very close to the optimum that you want to show to the user. There are modeling approaches in literature, like you have a loss function, a complex one that captures a variety of aspects in there. Sometimes it can be tied to a specific algorithm. And again, I think you have no global guarantees like with the greedy approach. And also for the multi-criteria decision-making approaches, or for some other like popularity-based approaches, sometimes the problems are framed as a mathematical optimization problem, a constraint problem, to find the Pareto optimal solutions in that space. Sometimes, and this is not discussed a lot in the papers, this easily leads to scalability issues, because this is a complex problem then. Now, when you have the whole family of many papers where we have accuracy versus the rest, how do we measure? You can do offline. So what you have to do, you have to have an additional measure for the other objectives you have. So if accuracy measures, now you need, for example, diversity measures, and many people use interlist diversity. And again, you want to then trade off these two factors. But the challenges are also there that while there are many papers that use interlist similarity or diversity, it's not always clear if this is true, did this metric really correspond to user perception in a given domain, right? So, or would the users even notice that there is some increased diversity? Does the position matter, which is not a part of the ILS metric? And the next question is, now you have your smart algorithm to balance these metrics. So what's the right balance, right? Well, what's the threshold? It's what is more important. And usually you have some alpha parameter there saying 30% on diversity, but where does this value come from, right? And this is a much more difficult question, also in the case of calibration. So if you calibrate the popularity levels, do we know that users would like that? Do we know if popularity on average would go down? If they're only mainstream seeing lovers, then even go up, right? So here's fairness and biases are recent topics, and we recently looked at the literature and tried a first survey of what people actually do, and their references are given below. And sometimes these are used interchangeably, saying, okay, fairness is just the popularity of the things that you recommend, with the underlying assumption it's only fair to recommend these niche objects or artists that have not much exposure. could make sense, of course, in some ways. But it's a bit simplifying. Maybe you really have to look at the domain and application, because maybe sometimes some items are not popular because they're just poor quality or a poor value for money, if you think about the domain in e-commerce. So, and on the other hand, there's the highly visible paper by Netflix, where they say, oh, we do all these complex machine learning, but then we add a healthy dose of popularity to the recommendations to avoid recommending niche items, because people might be unfamiliar and not try them out. So, and also in this often evaluation, often there's an absolute fairness target. So there's the assumption we have a target distribution, like recommend 1/3 of the recommendations from the long tail, from the very long tail. But where does this assumption come from? Can we validate that, right? And in some ways, my feeling is once you have that all given, the target distribution or some threshold, achieving these goals algorithmically through re-ranking is almost trivial. It's not like rocket science, right? And what we found here in this survey of given research, we found there's a severe danger of what's called the abstraction trap by others. So we do too much offline without validating or considering if that really makes an impact in practice. And in this general field of explainable AI, this seems to be an observation that was made by others, not by us, but we find it also in recommender systems research. There are some works that try to measure with users in this accuracy versus the rest situation. Here's one study by Michael Ekstrand and other people from Minnesota and Martijn. So they showed recommendations to use in user studies, and they try to assess the subjective quality perceptions by comparing the output of different algorithms. And the interesting part here is now we have competing objectives that you measure. You measure novelty, diversity, and satisfaction by questioning the users after they see all the recommendations. And then you can see how these objectives relate, right? And the interesting finding here is if you look at novelty, so these arrows mean the influence that we assume, or there's some sort of causality. We may assume, maybe if it's just a correlation, but still, we have a negative number here. So if you increase novelty, you recommend more unpopular, unknown items in that study, it may negatively impact satisfaction. This can have to do with all the limitations of user studies and so on, but this is important to understand as well, to know how these objectives in the multi-objective settings, how they play together. Now, in that context, so this concludes more or less the question of competing quality objectives. A side observation here is, as we say, would more accurate models, slightly more accurate models, would they translate into better systems? And even if we expect this, well, what is the price for that? So for instance, now we have the most accurate models might be computationally very complex. They may be easy to difficult to develop, to scrutinize, to maintain, to debug. So there's a price maybe for that 3% in accuracy in some metric offline. Would that really be worth doing it in practice? And I think in the Netflix price, the winning solution wasn't put into production for a related, maybe not the identical, but related considerations, right? So there seem to also be other multi-objective trade-offs in terms of complexity of the algorithm and the gain that you get from them when putting them into practice. So this was the first of these three categories. So first we talked about their multiple objectives from the individual user, more or less, right? Now, and we also talked about there's consumer and providers, and this leads us to the competing stakeholders objectives. So we go beyond the individual user. Example here is increase the profitability while maintaining consumer satisfaction. And historically, most of our research is on the user side, increase the relevance of the recommended items, and the implicit assumption maybe is to say, look, if we show relevant items, users will find something interesting and they will come back. And this is a reasonable assumption. So there's this implicit assumption, just show consumer-oriented things, then this is good also for the business. But in practice, maybe the goal of the provider is more direct than just helping users find something, but they want to sell more or increase customer engagement or change consumer behavior to purchase more expensive things, maybe. So there's the organizational goal here. And then once you have that in mind, you have these competing objectives or a different type of multi-objective recommendation problem. And also he did some pioneering work in this direction in different ways in Robin. Examples, we have examples with two stakeholders. We have consumers and providers. So we had try to summarize some work on price and profit of our recommender systems. And like the example could be you have two items that you can recommend. Both of them have the same expected relevance or utility for the user, but one gives you more profit. So you might be tempted, like, let's show the more profitable one, the consumer is still happy. Or on the other hand, you maybe have a discount on one of the e-commerce items, and then you just recommend those items, which might increase your revenue, right? And so there's this two-sided thing that you might consider. There are special cases also, very difficult ones like social recommendation, whom to follow, and even more difficult job recommendation, and most difficult maybe dating recommendation, because there has to be some reciprocal match. So the person who is recommended must also accept or have interest in this other person. And how to measure the success of a dating recommender is, I think, less than trivial. It's more than difficult, really. What's really successful dating, also in terms of the business value for the platform, right? So this is a very interesting problems here. There's another topic which I think also falls under multi-stakeholder, even though it was never framed as such, where you have group recommendation. There's a long history of group recommender papers where you have the goal to, you have a group of friends and you recommend the restaurant to them, knowing their individual preferences. And these are the stakeholders then. And many of the papers we see in that direction, they were like finding ways of aggregating the preferences of the individual ones, have some aggregation strategy, for example, having these least misery or some other metrics to do that. The unique aspect in this multi-stakeholder setting is really that the individual group members at the end get there's the same recommendations. That's important. So we have multiple consumers seeing the same thing. And I think from what has been done in this research, what is really missing a bit is group decision making is a complex dynamic process with social interactions between group members, and it's difficult to abstract this into some arithmetic function to aggregate things. And the studies often show that it's not clear which metric to use. So it's really important, and I had some work mentioned here at least, we should study how people behave in such a setting in general before and this should inform the aggregation strategies we have. So overall, in that context, in multi-stakeholder recommendations, a lot of challenges. So it is really, we have no real world data. We have, in particular, if we have business data like price and profit, we don't have that. So we use synthetic data. We also have to make assumptions about the optimal value, so we don't really know. And the final thing here is that longitudinal aspects might be really important. So not just looking at a one-time recommendation, but look what happens for the different stakeholders if we implement a certain strategy for a longer period of time. And this directly leads us to the third category here, which is about time horizon related or temporal perspectives. It's like, for example, you want to optimize short-term click-through rates versus long-term customer retention. And so the background maybe is in some domains, it's very easy to optimize the KPIs of the business that provides recommendations. So I have 3 examples here. So for hotels, some depends, of course, on the business model. Recommending cheap hotels maximizes your revenue. People like discount and things, so you have more revenue maybe in some domains when you recommend more of this. For news, if you just recommend what's been published recently, latest celebrity gossip, everybody's interested, you get a lot of clicks maybe. Or you just use clickbait headlines and people will click on that. In music, you can just recommend Ed Sheeran to everyone. That's a very safe thing. People like it. Statistically, it's popular. So on average, it's a safe strategy. In the long run, for these 3 examples, and for hotels, you might not be interested in revenue, but in profitability. So you maybe want to promote rather the more expensive hotels, or where you have a higher profit margin. In news, people might be disappointed. They click on the clickbait and then they see it's not interesting or nothing special revealed in there. And for music, if you always recommend things people already know or what's in the charts already, people will not find anything. They know, okay, I can find that by myself somewhere else. I don't need some discovery here. And then maybe they stop the subscription because there's no value for them. And these aspects are very important, but there's almost no research or very little research in the academic environment. And we also reviewed industry papers on recommender systems from all sorts of domains. They were also mostly on short-term effects. They report sometimes from A/B tests for a few weeks, but we don't know what happens after these 6 weeks when they deploy the models. So there's very limited reports from industry as well. But we see, or this is wishful thinking maybe, that we see some uptake on the topic in recent years. There's various forms of simulation, so you can consider reinforcement learning or bandit-based approaches as some sort of simulation. And there's some even smaller, a very small set of papers on agent-based modeling, which is a decade-old technique here. These simulations sometimes consider multiple stakeholders. So for the bandit-based approaches, it's mostly about user reward. There are other things here, and there are also some papers, some first papers that look at the customer lifetime value of the recommendations, which of course, again, is based on a lot of assumptions and even more difficult. Here, I just list another bunch of reference here. There's some works I was also involved with and I would like to share here. There are studies that look at the reinforcement effect of concentration effect. So what happens with some algorithms, if you just recommend popular items to everyone, those items get exposure, they get ratings again, thinking again about ratings or interactions, which you then feed into the database, and then you train the models again, and they start concentrating more and more on these small set of items. And we did some simulation where we took a database, we tried out different algorithms, we created recommendations. Yeah. So the simulation was, you take a database, let's say Movilence data set, you train 7 models, each of them makes recommendations, you assume some users from time to time pick one of those recommendations, they rate them, put them back in the database, retrain, and so on. So, and then what this figure shows, it's not important to know the details. On the x-axis, we show the number of iterations that we recommend, receive recommendations, interactions, observe interactions, and train again. And on the y-axis, we measured the Gini index, which is a measure of concentration or inequality. So when there's a higher Gini index, it means the algorithm tends to focus on a small set of items, so it's less personalized than others. And the main message here is that all these lines correspond to different algorithms. The main message is that the different algorithms behave differently. Some have the tendency to concentrate more and more, like popular item recommendations, whereas others often recommend, they broaden the spectrum of what's being recommended. So it's not important to see the absolute numbers because it's a simulation with assumptions, but you see the development over time, and there can be differences. An interesting observation here is, it's another difficult chart, but if an algorithm concentrates or not, or it's diverse or not, depends sometimes on specific hyperparameters that you use. So the important part here is you see the orange line, which is not fluctuating a lot. This is the RMSE that you optimize. So, and then the x-axis, you have training steps, how much time you need for training. And you see this goes down a bit and then goes up, and then it stays constant. So, so you can stop training at any time you want. The differences in RMSE will be very small, right? That's the message here. But you see the other lines, like the green one is diversity. This fluctuates a lot. So there's effects that you would not notice if you look at them, if you just optimize for one objective. So it's not that you can say this algorithm is particularly good for diversity, but you really have to look at the specific configuration that you deploy. We did the same approach for session-based recommendations, where you don't have long-term user preferences, but only a few clicks, and then you recommend within the session. And we found we also benchmarked different algorithms. And again, the model was, the simulation is, you start with a database, you start recommending, you assume some interactions, and then feed that back and train again. And what the main message here is, we had simple methods here, like a nearest neighbors approach and deep learning based approaches. And often they are quite similar in terms of accuracy. But what you see is that, again, they can be quite different in terms of how the reinforcement happens over time. So again, also for the session-based ones, where you just have these small short-term interactions and not long-term profiles, the same problems can occur. Then for another example is by Gedas and some other colleagues from this community about longitudinal effects, and they used agent-based modeling. So it's a different approach where you have agents that interact. Agents are consumers and the provider. And what they revealed is a performance paradox through their simulations, where they found if the users rely a lot on the recommendations, the added value over time decreases, right? So they maybe because they stick in their certain spectrum of what the recommendations do. And So the consumption diversity decreases, as like this is in line with some previous slides there. So the algorithm tried to concentrate on a few items more and more over time, and then diversity goes down and the consumption diversity in turn goes down. We did a similar study very recently where we looked at consumer and provider value, not about consumption. So we made some assumption, what if we recommend items that give more profit or items that are more relevant to the user, and the strategies in between that try to balance things. So we had these agent-based models, one provider and like 600 agents, like from a Movilance data set, every user could be an agent. And we assumed every item that you can recommend has a profit margin, and the provider can either focus on profit or on consumer relevance and everything in between. And we try different strategies. The simulation then goes as this. That's so the agents receive recommendations from the provider. They make choices from time to time. They pick one. They assess the utility of the recommendations with a particular logic, and they feedback their feedback to the provider. And then when we see retraining from time to time. And the important part here is if the relevance for the users decreases, so it's mostly profit oriented, so it's not too relevant, then internally each agent has some sort of trust in the provider. So if you get poor recommendations, only profit oriented ones, the trust will decrease, and the consumption probability, which we model internally as a state, decreases. And when it decreases for all the agents, then the overall profit for the provider reduces over time. Okay, so this we tried to simulate, and here's just again some outcomes here we measured. So the colored lines correspond to different strategies. So the black one is just purely profit-based, not personalized, just which is really a bad lower bound. Just recommend the highest profitable item. And the other one, the blue one is consumer-centric, means only the most relevant one, like a single stakeholder objective. And then you see on the left-hand side, you see for the consumer-centric one, the consumption probability goes up, and for the black one, probability goes down. In the middle figure, you see the profit per time step. So every iteration or simulation round, you get some aggregated profit. On the long-term development on the right-hand side, you see that I think a consumer buy strategy in the end is the best one that you can see. Of course, the absolute numbers are not so important. So with agent-based modeling, you're not measuring accuracy. You want to study emergent effects when you change different strategies and tendencies that emerge from here. Okay, now we have gone through these three parts: competing quality objectives, multi-stakeholder, and temporal aspects. Another thing, if you go back to the groupless system, what about user experience, about the whole system, right? And there's also multiple objectives there, so we don't think about a lot. So you can design user interface in different ways. For the first question is, how many items would you show on the screen, like 3, 5, 7, or before scrolling, right? And this is a trade-off maybe between information completeness and information overload. If you show too many, people might not be happy. If it's like 3 items to pick from, they might be not happy with their set of choices. Now, we said in some situations it's good to show explanations, like if you have multiple competing consumer wishes. So what kind of explanations do you show? Complex ones, simple ones. So there's transparency through the complex ones, and trading off cognitive effort for the user to understand those. There are papers that even say not only show explanations what the system did, but also allow the users to manipulate things. So say, no, I want more profit-oriented or more whatever I want, or more cheaper restaurant. Then you even have this sort of user control, which again might increase the cognitive effort. Or on the different level, we have here flexibility versus efficiency. If you think of these modern conversational chatbots, you can have a natural language input interface, or you have forms, just saying, okay, cheaper or more close by. And there's been some studies I mentioned here that try to understand the trade-off, what is good for users here in terms of the user interaction. All in all, and this more or less concludes this part. This is the taxonomy that sort of come out of this when preparing this talk. So we have these qualitative objectives: individual aggregate, multi-stakeholder, 2 or more, time horizon, short, long-term, user experience objectives with all the trade-offs. And the other thing I mentioned, it's termed system-related or engineering-related, maybe, or production-related, I don't know. It's sometimes, for example, is accuracy versus scalability, or model complexity versus the gain that you get in accuracy. So to sum up, so in practice, we see that recommender systems may not be a single objective problem, maybe in most cases. we have these different categorizations and multi-objective recommendations as approached in this workshop, thankfully, can really help to have more impactful papers and research in academia with all the problems which we have these real-world data sets, so we need more industry cooperation. Simulations may help in some ways to study emergent phenomena, but yeah, there's a lot of limitations and assumptions here. And the most important thing, maybe whenever we go for, let's say, multiple objectives, let's make sure we optimize for the realistic problems that help us get more impact in practice. Okay, so thank you very much for the questions. Again, here are the slides and the extended abstract, and I have to leave after the talk. So, but we have time for question and answer. Thank you very much.
Thank you so much. We have a couple of minutes for questions. If anyone wants to ask the question, let me know.
Hello, thank you for a very nice review talk. I'm curious about the intersection of multi-objective optimization with advances in causal inference such as surrogate index. Is surrogacy assumption and surrogate index one approach that solves multi-objective optimization? And if not, what are the shortcomings? Yeah, so I fear I'm not an expert to answer this. So I know there's a lot of important research on causal inference. I think there's a relationship that's not, I didn't figure out yet. So it's a good pointer. I was thinking about incorporating things, but I have no solution to that yet. But I think it's an important missing part from current research. Yeah.
Thanks again for the great talk. I have a question about studying and researching the research area around multi-stakeholder. As you said, you don't have access in academia about a lot of the information. We use lots of simulation. How can industry help? Let's say if we could release a data set somehow. Is this about like distribution of profit-based, or anything comes to your mind that can help academic research?
Yeah, this is one possible step, that you create synthetic data that reflects distributions and interaction patterns that you see. I would even go one step back, that if industry could share what are the objectives in reality. So we don't even know what, like when you see industry talks, often there is a comparison of algorithms, and then you have the y-axis, and you don't know what it is on the y-axis. You don't even what the business measure is. If we just even know what the business measures would be the key objectives, we can look for computational proxies for that, but synthetic data would also help, of course. Yeah.
Great. We also have an online question. How do you find if your objectives are competing or correlating, since data might be biased due to exposure single objective optimization?
Yeah, we don't know. That's the problem of current research, which is not directly tied or limited to multi-objective optimization. If we have a lot of data sets, we have no idea what the data, how it was collected, and how can we be sure that this makes any sense. But this is a more fundamental problem. Even before we go to multi-objective, even for accuracy, we don't know. If you think of Last.fm data sets, if they were recorded from the Last.fm radio, which plays automatically, you reconstruct the radio, right? So there's a lot of exposure bias, or what the algorithm does that was in place. So this is an important problem, but it's not tied necessarily, I think, to multi-objective. Could be.
I had a question. This was a really nice talk. I really enjoyed it. One of the things that we have done at LinkedIn is considering the objectives on the different sides as linear functions, and then try to set up a large-scale linear program which can trade off the objectives against each other. But this technique does not generalize to arbitrary kind of functions, and also is a kind of a post hoc step. So you would have to calculate the objectives on both sides and then start trading off. Do you have any suggestions on how it can be more organic as you are solving the original problem itself?
Yes, I'm not sure I understand the original problem, but I understand you have a specific approach for your given situation. So I think that what we should also do more in general, really try to solve specific problems, specific settings, and then try to generalize. So if we just come up here, let's have a generalized model or approach, how can we be sure it's general to what? So I think if you understand correctly, you did some work for a specific setting. We should do more of such settings and see what transfers to other problem settings, and then generalize and find those solutions.
Thank you.
We have time for one last question.
Thanks for the talk. Ultimately, there's multiple objectives and everything, but it comes down to the question of power, right? So ultimately, it might be a single objective system just based on who has most power to push through what they want. So how can we study that, or how can we get this into the research? This kind of question.
So I didn't. Who has what power?
No, like it ultimately becomes a question of power, right? You have all these different stakeholders, these different like objectives that are in the system, but which of these actually become relevant in the real world is not so much a question like what do.
But again, I think that what comes to my mind, it depends again on the specific business model. So the typical example is if you have the hotel booking platform, and they have the property owners who want to be listed and have exposure. The platform wants to make a commission through sales, and the consumer might also have different competing objectives like price and location. And then it has to be a balance in this market, right? If you ignore the property owners' wish to be shown or exposed, then okay, they will not list their hotels anymore, maybe. So maybe maybe it balances from itself based on the business consideration in the long run.
Thanks.
Thank you so much again. Let's give it up again for our keynote speaker.
Thank you very much.
So we have a presentation. Let me. Making smart recommendations for perishable and stock-out products by Sinan Seymen, Anna-Lena Schoch, and Edward Malhaus. Is any of the authors? Sinan, please. Also, just as a reminder for the authors that are in the room, we decided to go with one laptop only to avoid any problems. Please send your slides to my colleague Zahra Nazari to this email address. Where was the slide? This email address, zahra.nazari@gmail.com. Okay, so Sinan, please. Actually, you have it.
Can I do it in the presentation mode? Would that be fine? There are the 3 dots. And present mode, if that doesn't okay. Okay. Can you hear me clearly? I'm guessing. Okay. Yes. Cool. So, hello everyone. I'm Sinan Seymen. I'm a PhD student at Northwestern University. Today, I will present our paper titled "Making Smart Recommendations for Perishable and Stock-out Products," and it's a joint work that I work with Anna-Lena Schoch and Edward Malhaus. Firstly, I will go over the introduction, then we will talk about the model we propose in optimization setting, then I will finish with results, conclusion, and future work. So 1/3 of food is lost or waste, and avoiding this loss is becoming a global challenge everywhere in the world. Only in retailers, 28% of the items are perished just because they expire, just because we couldn't find demand to any of the users, and we need to throw them away without any other flaws. And we can say in simple terms, food waste in retailing occurs when supply exceeds demand. And maybe one simple solution would be to decrease the supply so that we are not going to exceed our demand. But there are a couple of problems with this. Firstly, we don't really know what the demand is. So we might have an idea what the user might want in the next day, next week, but we aren't sure. The retailer doesn't know exactly what the user will want. And secondly, if we try to decrease the supply too much, we will encounter stock-out problem. And then the user won't be able to get the item they want, and it will incur a loss of goodwill, and retailer won't be able to profit. So they don't want that as well. So in our work, we were thinking, how we can utilize this customer demand to alleviate these problems. And then our approach tries to incorporate everything in recommender system, inventory management, and promotion literature. So we are thinking, how can we use these recommendations? So recommend items to users in a way that can we alleviate the soon to perish items while not incurring stockouts, which is stockouts are becoming a big problem again with firstly COVID-19 and supply chain disruptions, and also in some part of the world, the climate change. There are a couple of works working with like these sub-problems. One work proposes a recommender system model with perishability, but without stockouts, because they are considering a deterministic setting. And when I say deterministic, I mean they know what the demand is, they know what the inventory is, they assume they exactly know how many items will perish. Another work in the literature proposes a recommender system model that lowers stockouts without perishability. And in inventory management literature, they work with perishability and stockouts at the same time, but they do not include user ratings, or they don't really offer items to users thinking what the utility might be. So our contribution is trying to solve all these sub problems in like multiple stakeholder setting, which everyone has a different objective. User wants to get relevant items to them, retailers wants to make profit. And we incorporate perishability and stockouts. So while trying to make everyone happy in the system, we also try to lower the number of perished items and number of stockouts. Our method is a mixed integer programming optimization model. And as far as we know, all these 4 sub-problems I have discussed, we are the first model that solves them simultaneously in a stochastic setting. And we also offer heuristic approaches to make our model more scalable. So if the numbers of items and users are allowed, we still have an approach offered in our paper. And then I will talk about the results of optimization, heuristic, and the benchmarks. So I will go over the details a little bit fast, but basically demand is denoted as D, inventory is L, and soon to perish items are E, and retailers are purchasing their items and selling them after putting markup on top. And when I say we are working in a stochastic setting, we assume inventory levels, demand, and soon to perish items are all uncertain. We might know what the mean is, but we are generating scenarios using Monte Carlo sampling. And we generate as many scenarios as you can see in the slide. And in every scenario, there's a realization of inventory for every item, how many items will perish soon, and what will be the demand of item I to user U. So this is our mixed integer programming optimization solution. Again, so in this setting, we have constraints, and basically we will have a solution that will obey the rules we have set. And I will discuss the rules we have put in this model. Firstly, as you can see, we have a lambda value that maximizes the average scenarios. So we will at the end find a recommendation list for every user, including every items, that maximizes this objective function value considering all the scenarios we have generated. In the left side of this objective function, we define user perspective. So user wants to maximize their utility. They want to get relevant items recommended to them while not having stockouts. Because we are thinking, if we recommend lots of relevant items, but when they want to actually purchase the item, if we are saying this is out of stock, it will still be penalized, and user, we assume, will not be happy about it. And retailer wants to increase their profit while decreasing the soon to perish items. And we are assuming this because perished items are lost to the retailer. They would rather sell them right now rather than just throw them away. So quickly, what the constraints do, equation 2 forces the solution to have at most k many items recommended to them. So every user have at most k items recommended. For example, in an online retailer setting, they might have an email saying 5 items. Do you want to purchase again with us? Kind of emails, and these are the lists. And we will recommend at most k many of them. We force the model to not sell more than inventory, or soon to perish items will perish if not sold. And the equation 5 is the inventory balance equation. So one problem, even in the keynote we have discussed, mixed integer optimization models will have a scalability issue. And there are like some solutions to this problem. You either want to reformulate your model so the number of decision variables and constraints are smaller, or you might incorporate some other heuristics to make the problem smaller. And in this paper, we try both. And our reformulation ideas are used by Dancing and Ferguson's papers that you can read. And this is the reformulated idea. Again, I'm not going to go into the details, but the main trick is we can get rid of some of the decision variables by reformulating this previous model differently. And in equation 9 and 10, we still have constraints, but they are very easy to understand for commercially available optimization software because they are simple upper bounds and they do not require the same memory that the preliminary model requires. So comparing these two models with the preliminary model, it's more intuitive to understand, but while creating scenarios, we can only go up to maybe 3 or 4, and then we will have memory issues and speed issues. In reformulated idea, because of the tricks we have applied, and in the paper we have more details, we can go up to thousands of scenarios. And then we can solve, we can offer a solution that solves all the scenarios at the same time. And this is the heuristic approach similar to the reformulated idea. In equation 7, you can see the only difference is this is a myopic approach and we offer the best item at this point. And at every step, we are offering the best item. And again, this is a myopic approach because it doesn't mean it's the optimal solution. At this step, one item might maximize this objective function, but at 5 steps later, maybe that item shouldn't be in the list anymore and shouldn't be recommended. And we have another work actually proves this, how optimal solution can beat heuristics in every sub-problem. So in data preparation part, we are using a real online retailer and we are using their last 6 months of data available to us. We have 4,000-ish users and we aggregate some of the items as in products brand name to get 4,000-ish items. And from these 4,000 items, we have 600 soon to perish items and we apply best N method. We call it best N, and we offer the best N users to every item and best N item to every user. To considering the utilities we have, we are thinking maybe we can shrink this our model even more so the scalability improves. And we calculate all the item user ratings using SVD and the previous demand of the users. And we create soon to perish items by this equation, Li times Ci. Ci is the probability of perish. So we are assuming if this is 0.5, we are saying 50% of the inventory will perish at this time frame we are working with. And then we generate the demands and the inventory, again, considering the 6 months of data and assuming some D bar, which is the average demand that might happen. And then we generate our scenarios using Poisson distribution for demand and inventory and normal distribution to find soon to perish items. We work with 4 different benchmarks that solely optimize each sub problems I have defined. So there is benchmark perishability, benchmark sales, benchmark stock outs, and benchmark user. And we generate 4 different settings that are considering high perishability and low stock out risk. So if it's high perishability risk, basically we are assuming probability of perish is larger for soon to perish items. And if it's low, other way around. And if it's low stock out risk, we have lots of inventory. And if it's high stock out risk, we generate scenarios considering less inventory. And these are the metrics. Again, user perspective is calculated as ratings minus stock outs, and retailer perspective is sales minus perishability. So I'm also, okay. So in our solutions, again, the paper has a lot more in-depth conclusions, but I will only talk about the interesting results or takeaways. So firstly, interestingly, benchmark user is doing worse in user perspective. So if we only offer items that the user utility, maximizing user utility, we notice that we will have significant amount of stockouts. So if we are only trying to make the user happy, they won't get the items they want. And because of the stockouts, they will be actually very unhappy at the end. And we see that in HL setting, high perishability, low stockout risk, we have the worst outcome for retailer. And this happens because if the retailer buys lots of inventory, a little bit too shy of stockouts in a high perishability risk setting, they won't be able to sell a lot of the items, even using recommender system ideas. Even if you recommend a lot of items to everyone, they still won't be able to sell all the soon to perish items, and they are significantly worse compared to every other setting. And we also see that benchmark sales performs worse in user perspective when stockout is high risk, and in retailer perspective when perishability is high risk. So BR is benchmark sales, and they still, while having profits, they also consider the users as well, because while trying to make profit, you want to offer the items that the user might actually want. But still, in this setting, they perform worse than our optimization solutions, which in these slides, I've put 01, 05, and 09, and that's the trade-off basically being 0.1, 0.5, and 0.9, which is a little bit user-sided, equal weight, and a little bit retailer-sided. And benchmark perishability performs worse than our optimization models in user ratings and sales. Again, if we go the perishability route too much, then we are going to offer items that the user actually do not really want, and the retailer will not be able to make profit out of it. I guess this could be considered as recommending everyone bananas, apples, maybe they will just perish and I'm just going to offer them. And then still the user and retailer actually won't be happy about only focusing on one thing. And again, we can see here, benchmark user will have lots of stockouts in there, and perishability is very high in HL setting, because like I said, inventory high, perishability high, it's the worst case scenario for the retailer. So then we compare our heuristic and optimization solutions. It's heuristic H1 to H9 and optimization 1 to 9. And we see that the heuristic approach also works well, and heuristic approach usually loses 1% of the objective value in total. So if someone doesn't care about that 1%, and you are more interested in more speedy solutions, or you have memory issues, or you need to run this all the time. So again, speed is a crucial part of the model. Heuristic approach still does well. But if you can afford it, you can also only run the optimization solution, and it will take a little bit more time, which is 5 to 10 minutes, actually less than 5 minutes in thousands of users and items. But still, that might be a deciding factor. And this 100 and 500 is the best N approach. So we also see, at least in our data, so this is the data dependent, only considering top 100 items and users are not that bad compared to 500. So we are, again, thousands of items, users. If we only consider the top 100, we are not losing that much of the objective value. And then we also check the number of scenarios generated, and if actually we need to be in the stochastic setting. And model A solves the same problem with the expected values, and they get outperformed by the optimization. So we say that, yes, if we work in stochastic setting, and if we deal with multiple scenarios that might have different levels of inventory demand, etc., we are getting actually a better solution that suits to all of them at the end. And using expected values for everything actually is significantly worse than creating scenarios. And yeah, in our future work, we are thinking maybe applying our model over time and getting customer feedback to maybe fix some of the assumptions we are making, and go to the route of large-scale optimization techniques and just get rid of all the heuristics and maybe have it scalable only and get the optimal solution as well. And yeah, thank you for listening.
Thanks, Sinan. Any questions from the audience?
Did you test like different sizes of the data to hit a point where like you couldn't, couldn't actually solve it just because it was too big? Is that
So yeah, we have tried some simulated data with users items. We have never hit that part with hundreds of thousands of users items, because then we could always use the best N approach. In a way, if that user or item number is getting too large, we can shrink the data still using the best N approach and maybe consider top 50 items and users to alleviate that memory problem. But yeah, we have worked with different simulations as well to see that.
okay?
Thank you.
Any other question? I have one question. So I found this very interesting in general, because as you mentioned, this is one of the examples that if you optimize precisely for user preferences, at the end, even users might not be happy. So this is a very good, interesting example of multi-objective recommender systems. And we might have the same issue in other domains. For example, let's say online dating, that everybody might like to have a supermodel, but the supermodel wouldn't be happy and the users wouldn't be happy either, because they wouldn't be accepted by the person who is recommended. So do you know, like maybe there is some type of characteristics of different domains or the type of items that makes this problem like that? Like basically what type of characteristics exist in those situations that even optimizing for user preferences will not make users happy?
Yeah. Maybe I feel like I can say every domain has this problem, because again, it comes with actually it could be in some domains considered popularity bias still, because we are only offering those items. And most of the time in industry, as far as I can tell, we are using the same models over and over and we are updating them. And if we are keep offering the same items over and over, we will add this bias. And again, some of the items will be just drawn out. And I feel like it's definitely very easy to see if we have some sort of inventory or some sort of an upper bound, but I feel like again in popularity bias it could be a problem in every domain in recommender system setting.
Thank you. Let's one more time give it up to Sinan.
Thank you.
Our last speaker for the session is going to be online. From the online organizers, do you know who is gonna?
Iman, I just sent you the name for the next speaker. So I do not have
speaker,
Actually,
the next paper is PM Keylight GCN, optimizing for accuracy and popularity match in course recommendation, by Yiding Ran, Hang Cheng Hu, and Minian Khan.
Yes, I'm here. Can I share my screen?
Yes, if you can share your screen, please do so.
Okay, sure. Can you see it?
Perfect.
Okay, can you hear me clearly from the workshop?
Yes, we can see the screen. If you could speak a bit louder, that would be perfect.
It's not better?
Oh, okay. Increase the volume from the laptop.
Thank you so much.
Where is? Oh, I see. Perfect.
Okay, thank you. Then I'll start my presentation. So good
Perfect.
morning.
Yes, you can start now.
Okay, thank you. Good morning, everyone. I am Yiding, and I'm here to present the paper titled PM Keylight GCN, Optimizing for Accuracy and Popularity Match in Course Recommendation. This is a work done by me, Heng Chang, and Prof. Tan. So most existing course recommenders optimize for accuracy. But the question we want to ask here is whether accuracy optimization can optimize user experience as well. The answer seems to be no based on an existing study. So when we introduce relevant courses that are previously unknown to the students, they are likely to prefer the new courses over the original course plan. The fact that they can improve their experience suggests that accuracy is not the best metric for user experience. So the question is, how can we incorporate both criteria in course recommendation? And we propose multi-objective course recommender with accuracy optimization as the first objective and user experience optimization as the second. So the question here is, how can we measure user experience? And to answer the question, we conducted a small-scale user study in which we found out that students actually demonstrated disparate interests towards elective courses. Some consistently demonstrate preference over popular courses, and others favor niche ones. So with that, we conclude that student satisfaction can be related to whether the course recommended has popularity that matches their interests. With that, we propose a proxy for user experience optimization. So we will be performing preference popularity match for our second objective. And the performance will be measured using a self-proposed metric, which will be introduced later. So now let's go into the first objective, accuracy optimization. In this study, we used a data set which consists anonymized listing of course taking history from our institution. And due to privacy concerns, both course ID and student ID are masked, so we do not know the exact student or the exact course. For our preliminary study, we experimented with some non-domain specific models, and we have some quite interesting findings. Both KNN models demonstrate uncommon superiority in the task of course recommendation, and we hypothesize that it might be possible that the nature of course consumption aligns with the underlying inductive bias of KNN models. So to better understand the strengths of KNN models, we compare it with the best performing deep model like GCN, and we identified two characteristics of atom KNN that contributes to its success. The first one is the importance of pairwise relations. The second one is the focus on close neighbors. So these two findings actually inspire our own model, K-like-GCN, which is proposed for the first objective, accuracy optimization. So here, for the first step, we will be computing a like GCN similarity matrix using the student embedding and the course embedding. Next, we will be computing the differences between these two sets of similarity matrix. One set is computed using like GCN embedding, the other set computed by the KNN models. Moving on, we are incorporating the differences computed into the original BPR loss, which forms our new BPR loss for this model. So this forms our revised like GCN component, and this revised component will be combined with the atom KN component that forms our K-like GCN model. So let's now see how K-like GCN performs in terms of the two accuracy matrix. So we can see that by focusing on both pairwise relations and close neighbors, the two characteristics identified, our model K-like GCN outperforms all in terms of the two accuracy metrics. So now let's move on to the second objective, preference popularity match. First, let me introduce how we quantify popularity and preference. So we define course popularity as the log of the average enrollment of a course. And student preference is defined as the average of the course popularity taken previously. Here are the distribution. We highlighted the top 25 percentile using orange, and we can see that a small group of courses form the very popular ones. And because students are taking very popular courses together with a small set of niche electives, we can see that many of them have a pretty high preference score. And also, we proposed a new metric called preference popularity match, which measures the performance in the second objective, which is preference popularity match. So this metric is computed as the average difference between the target student's preference and the popularity of the course recommended. So now let me introduce our multi-objective course recommender, preference match K-like GCN, which is designed to incorporate both objectives. So to achieve first objective, accuracy optimization, we will be taking the top 50 recommendations by K-like GCN for the target students. And then to achieve the second objective, we will be sorting these 50 recommendations based on how close they are to the student's preference. In the end, we will only keep the 10 courses with popularity score closest to the target student preference, and that will form our final recommendation. So here's the performance in both objectives. We can see that our model PMK-led GCN achieves a 70% reduction in the preference popularity mismatch at the sacrifice of only 4% accuracy. So it manages to achieve both objectives and achieves a well balance between the two. So to conclude on the study, we studied the special nature of course recommendation and identified two characteristics that are very critical to success in course recommendation. We also proposed PMK-led GCN, which is a multi-objective course recommender. However, these are only the tip of the iceberg. In the future, some promising directions include finding out alternative representations of student preference and also conducting more extensive user study to evaluate the model from users' perspective. Last but not least, I would like to end the presentation with a question posed by one of my reviewers. So how should we define the role of course recommendation in tertiary education? As course recommender researcher, should we cater the recommender to students' needs, or should we cater them to the needs defined by the educator? What are the implications in the bigger picture? So with that, I have come to the end of my presentation. Thank you so much for listening, and I'm open to questions now.
Thank you. Any questions?
Thank you very much for your presentation. And can you see any correlation between the number of layers for LightGCN and the metric proposed by you?
Yeah, sure. Thank you for the question. So regarding the correlation between number of layers in LightGCN and accuracy, we do find the correlation, which is that for other recommendation scenarios, it's common that when we increase the layer inside LightGCN, we can achieve a better accuracy, and the optimal number of layers is often 4. But in our task course recommendation, we find that increasing layer doesn't really contribute to higher accuracy. The optimal layer is actually 2, which actually leads to our first finding that the importance of pairwise relation, because at the second layer of LightGCN, we are capturing pairwise relations between students and between courses. So that's the answer to the question. We actually find that in this specific task. Yes, thank you.
Thank you. Any other questions? I have one question. So you used for the kind of popularity mismatch, or for the match, you measured average popularity of previous courses taken by a user. Did you experiment with some other measures, for example, not the average popularity, but kind of the ratio of popular items, since the average might basically get kind of distorted by few super popular courses, and that might make something a bit kind of difficult. Did you experiment with other metrics?
Thank you very much for the question, and that's a very valid one. We didn't manage to explore with other representations of student preference, and we actually identify that as one of the possible future work, and also one of the limitations of our current work. Because as you have stated in the question, that by representing student preference as the average, we indeed may result in some underestimation of student preference, or the measure may be kind of affected by extremely popular courses or extremely niche courses. So one of the possibilities we are thinking now is to actually maybe represent it in terms of a distribution, so that we does not only capture a mean, but also capture the variation in the course popularity.
Thank you so much. Thank you again for your presentation. Please give it up again for our presenter. And with that, we finish the first session. We have a half an hour break, and then we will be back at 11 this morning. Thanks, everyone.
present this. She was injured again.
I'm sorry, Zahra. You're muted, I guess.
Thanks for the heads up. We didn't say much. I just was introducing the speaker, Peter, who will be presenting proximity-based educational recommendation and multi-objective framework.
Okay, good afternoon, everybody. I hope you can hear me really well, because I'm going to speak in a mask. Don't ask me why. Oh, you can ask me why later. So it's exciting that I can present here. Apology for I only joined after lunch, but I'm going to stay till the end of the workshop. And this is a joint work with Chun Pai Wang, Shahaya Sahibi, not pronouncing it right. Zahar did it much better. But I can pronounce my name, Peter Brusilovsky. I can do it better. So it's a joint work between Albany and University of Pittsburgh. And I think it presents some interesting case of multi-objective issues in educational domain. So hopefully it will be useful for everyone. Oops. So I'm going to talk a little bit about motivation, why we're doing that. Then I present our framework for multi-objective recommendation, which we call PEER. And in the back number 6, actually, I remind you, you can get peers for your lunch. And then talk about data set and present the result of evaluation. I'll also try to show you a bigger picture, because we're kind of working a lot on multi-objective things, but the angle of my personal work and my group is not exactly the same as presented in the paper. So I'll just throw in 1 or 2 slides at the end. So multi-objective is really very critical, because there could be multiple reasons people can get recommendation and multiple stakeholders to get recommendation. And in education context, it might be very specific. So what is about education recommendation systems, and what could be really multi-objective? Education recommendation systems are very popular, and there are many of them. And we talk about one specific type of that, recommending learning content in free online practice system. Students basically learning by doing. And unlike a mandatory content, you need to get a lab, you need to do readings, you need to get homework assignment. It's not enough practice. So lots of people really learn by practicing. They solve problem. And every textbooks provide you at the end of the chapter a bunch of practice problem to solve. You're not getting grades for that, right? But that's the way you learn. So now in educational domain, a practice system become more and more popular, because practice is the best way to do adaptation. Everyone goes through the same set of assignments, right? Because it's unfair to give more assignments to weaker people. But in practice, weak people can get much more work, and even more, this work can be focused on their weaknesses. So everyone, while doing the practice, can focus on something they need most. So it's the greatest case to engage recommender system. So the way to do it, so the student look at a bunch of potential learning content, mostly problems, but also worked out examples. They work with the content. It might be success or failure. The recommender system takes into account, do the modeling, and recommend something next to do. It's kind of, in the old good days, this was known as sequencing, because at that time, the word recommendation was not known. Now everyone talks about content recommendation. Just to show how it may look, and I will get back to the same picture a bit later. So here, a practice system for learning Java, as I see. Students can see multiple topics, and within each topic, they can click on a topic and look at a bunch of potential activity to practice with. It might be worked out examples. It might be several different types of problems. And once they work on them, they kind of see what is solved, what is not. And what is not solved might be good for them or bad for them, but they can get recommendations. So there's a bunch of things for you to do in the topic, but that apparently is the best according to the recommender system. In this specific context, we're not just showing the ranked list, we show the recommendation in context as well. So you can see where this recommendation is located. You click on a link and then you get to the right problem to work with. So that's the way it potentially can look at adaptive practice system. All right, now, what are the challenges of recommendations? There are many different sequencing policies, and there is no agreement how to do it right. If you go to the old good days of behaviorist approach into education, which has been established by Skinner, much criticized now, then the idea is that get you something which you have very high chance to solve. Because once you solve it correctly, you get positive experience, because if you fail, you get negative experience, you not learn. So the idea of Skinner to give you very easy steps to the next problem, give you something easy. The idea of modern systems is optimize your learning. We like to get your knowledge as fast as possible. So as a result, there is an opposite trend, which in fact we also explored in one of our work, but not just us. We have this work called knowledge maximizer. Among multiple possible problems, we'll choose the problem which gives you maximal potential knowledge increase if you solve it. But that's actually the opposite thing, because if you fail, it was kind of a very good bet, but it's not going to be good experience. So apparently something really should be in the middle. It shouldn't be very easy to solve, but it should not be very hard to solve either, because then you have a very hard chance to fail. And if it's a failure, it's not positive experience. So very natural to think about that. We need to get a kind of precarious balance. On one hand, should be good enough, on one hand, not hard enough. And a very good guidance for us is provided by, where's my slide about that? By zone of proximal development. I guess I skipped that slide, which tells us, maybe actually, no, it should be there. Yeah, okay. Very good guidelines provided by zone of proximal development. This is done from work of Vygotsky. This is the shady area between what you can do really well and what you can't do at all. Originally, zone of proximal development is something which student can do with the help of a peer or instructor, something which doable with extra help. In our case, extra help provided by recommender systems. So how we can do it at all? Well, we need some kind of knowledge engineering. So in our case, knowledge engineering consists of 3 parts. Part number 1, we need to build domain knowledge model. What domain is about, what kind of concepts are in the domain, what are the skills. So here, this bar represents, every bar represents a concept of the domain. Thing number 2, we need to know how much students know about each concept. It's called student model. Here, the size of the bar represents specific student knowledge about the concept. You can see something is not known at all, something known reasonably well, and something actually negative. This is a specific knowledge model, probabilistic one. What is underneath red is less than 50% chance that you know. Everything is an estimation. Finally, for every problem, we need to know what kind of skills this problem allows you to practice. And this is done, for example, in this case, if you click on a problem, you can get concepts related to the problem highlighted. 1, 2, 3, 4, 5 concepts. And you can see it might not be a bad problem to solve because there is something not known, but a bunch of other things are known. That's a kind of combination of good, weak and strong problem. All right. So given that context, what we're trying to do, we try to get you a recommendation as long as you solve a sequence of problems. You solve a problem, yes or no, success or failure, we take into account and get you the next best thing to do. As I mentioned, the idea here is that a zone of proximal development, something in between the very hard things to do and very easy thing to do. So to make the problems and student knowledge on the same page, we represent student knowledge as a vector in the multidimensional space. The dimension is the number of concepts in the domain. We represent learner knowledge also as a multidimensional space. So with that, we can potentially match the problem to the learner knowledge. How we can try to figuring out a balance between hard problem to solve and the useful problem similar to your knowledge. Well, similar to your knowledge is very easy to do. We basically can connect the vector similarity. Here is your knowledge is a vector. For every concept, there is a probability you know that. Here is a problem. For every concept, there is importance of this concept in a vector, right? If it's similar, the problem exactly matching the level of your knowledge. Well, it's probably not a good idea because there's a very high chance to solve it. On the other hand, we can calculate how much you don't know about a specific concept, right? The more you don't know, the harder it is. So that's another vector which can estimate to what extent the problem will be hard. So strike the very balance, we get a very simple approach, which might be much more complicated, but we get just the multiplication of two estimation. The similarity estimation, which is mean how easy the problem is, and the complexity estimation, the lack of knowledge, right? This is the level of knowledge. 1 minus level of knowledge is the lack of knowledge. So how much knowledge is lacking? If it's very large, lots of knowledge is lacking. So I'll hope in this simplistic approach that this multiplication is balancing each other. So that's basically the idea of the peer framework. So every time we calculate knowledge, and we produce that estimation for every problem of a balancing score, the peer score. And then we just rank the best problem according to the peer score. The best ranking problem has the best balance, right? So we're not estimating how hard them or how easy, we combine. So good ranking is a good balance. All right, I guess I skip a few things because I'm getting a bit slow. How that look in our case? So we have, as I mentioned, we have a very large data set, large set of problems. From this data set, we collected traces of multiple students. So the paper has shown how many students data were collected. So this is the kind of the system the students work with. They didn't get recommendation when they've been solving the problem because recommendation influences what they do. This one, don't ignore it for now. They don't have that help either. So they've been working with the system completely on their own. Click on a topic, see what problems are with the topic, choose it by yourself, and then success or failure. So we get trace of the student problem solving, more successful and less successful, and it is our data set. So how we can estimate to what extent student did a good job or not good job? Well, for every student, we have a pre-test and post-test. So this is distribution of the pre-test, this is post-test. And also we can estimate knowledge gain. Knowledge gain in educational system is considered to be success of the process. So as you can see, students learn quite a lot, but not everyone is learning equally. Some people get very large knowledge gain, some considerable, but almost everyone learn at least something. So this is a good data set. So we can, on one hand, different students have different knowledge gain, so we can see differences. On the other hand, it's not a failure. So that's why it's kind of nice to use data set. So now, how we can do evaluation of our approach? That's actually challenging question. I may react to that separately, but the deal with, we use simulated students, and doing simulated student is a very big challenge in educational situation because simulation might not be reliable and just. What do we mean just? Frequently, when you design an approach, then you design it understanding some way the student behave. And then if you evaluate it against the same simulation, not surprised that your approach is great. You design with the same idea of student modeling like you use. So the fair approach is so-called robust relation matrix, which means you have multiple approaches to model the student, and every approach is going to be evaluated against every policy. So that's what we get. So we get 3 different approaches to simulate students, to simulate their knowledge growth: BKT, DKT, and DQKT. Don't want to talk much about that. DQKT is our own approach. So, and we need to build a matrix, every approach against every policy. In fact, we can get even multiple policies for the same approach. So we get 3 simple policies of sequencing, which is random, just get any and solve problem. Instructional, which is going to the problem the way instructor ordered them. It's kind of meaningful, but not the best for everyone. And anti-instructional, going oppositely from complex problems to the easy. Well, it's a kind of basically to get sanity check. If our opposite things are not working really well, maybe there is some reason that our evaluation is good. Now we also get several different policies related to the knowledge estimation. So we get maximum, we get mastery policy. This policy is only available in models which can estimate level of user knowledge, not only predict success or failure, but estimate how well user knows things. And as a result, not every policy is working with every model, but we get quite a number of them. So in total, we have quite a lot of different policies. Every policy has in conjunction with some kind of model, but we're going to relay them against every other single model. That's why it's a matrix. So this is BKT, this is DKT, this is DQQT, this is BKT, this is DKT, right? So that's why we're not evaluating BKT policy-based using BKT simulation. It might perform too well. So that's the approach which kind of being agreed in our field. So, well, what we get at the end, I might be scrolling to the end, is that indeed our combination of policy turns out to be the best among at least these meaningful policies. We also can do our sanity check. It does look like the random and opposite sequencing policy is working worse, which probably means that our evaluation makes at least some sense. And we also confirm that among the other kind of policy, the policy which is not getting you the worst meaningful options are performing the best. So this is this one. All right. So that's the maximizing the uncertainty. All right. So we repeated that results for shorter trajectories and for longer trajectories. For shorter, it works quite well. For longer, we can't just say whether it's working or not, but there are about 105 problems. And we try to do trajectory with 100 problems. It's kind of not fair evaluation because many problems will be repeated. So that might be the result. Our failure in 100 problems will be very natural. Okay, well, now I'd like to say just one more thing. Multi-objective evaluation, there could be multiple reasons. Who should decide how to balance the reasons? In our work, we presented you this kind of balanced approach, multiplication of two reasons, balances score. First of all, it might be other way to balance, harmonic means. But other approach, which we explore in our group, can we just ask the students to do it? So we have another experiment. Now I can tell you about that scale. Students look at the problem and can see the estimation of the probability. And then it's up to the student how much you can risk. Are you like to rush forward with really complex things and gain a lot? Or you like to play safe, right? And get an easy problem, but solve it for sure. So it might be the approach. But even with that, having a policy which can balance these two different sides as a very single number might be easy because it's much easier for user to use a slider. We might not be positioning our slider where we need, but with slider, with the same kind of, which can be provided by peer evaluation, it might be still beneficial even for user control case. Thank you very much. Cool. So, sorry, we started late, so that's why I take some extra time, right? All right, now questions. I skipped through some parts, but please ask me a question about the parts. I hope I expressed the most essential thing, the small subjective stuff in education and how we can evaluate it.
Really interesting talk. Do we have questions in person attendees? Okay, I have a quick question. It's really interesting. I've never actually faced the educational type of recommendation. Now I think about it, I'm working in podcast recommendation and music recommendation. You can also imagine there is this level of, for example, for taste in music, there is this acquiring taste that a lot of people talk about. I'm really wondering how we can use some of these methodologies, these approaches into other domains as well.
I think in music, you actually can do it because we know that the more we play specific type of music, the more we kind of like it. It's a very, very, very well-known psychological bias. So you can take into account if you trace, well, if you have some way to model the music, even concept-based or maybe like content-based, whichever way, it could be metadata or could be things extracted from the content like in Pandora. Then you can trace how much this music has been playing by a person. And then the chances here are that the music which has been playing frequently, the style of the music which has been made frequently might be more appealing for you than for a person who has not been playing it frequently. Now, is it really very important? Well, maybe not, because when person play the music frequently, we kind of think it's their interest. We've already taken into account the same thing, right? So we did the taste really evolves and it affects people, but it looks like current recommendation technology in the music domain already taken into account. But in other domains, it might be more challenging, like product recommendation, for example, right? The way that you take a product depends on what kind of experience you have with the product.
Yeah, and podcasts, we know from user research, users use podcasts mainly for educational purposes, actually.
Oh, yes.
There is content there. There is definitely acquisition of understanding and learning through time. So it would be very interesting.
That would be absolutely relevant, right?
Yeah.
So the things which are too complicated for people in the podcast would be really a problem. We're using that ideas from educational field when we recommend information for cancer patients. So it's not educational domain, but we need to have a chance to measure the knowledge of the cancer patients. To present them something very complicated to understand is not a good thing. For podcast, maybe the same thing. And you can do that by extracting key phrases, concept key phrases from the text. And if people has been exposed to specific key phrase, chances are they familiar. It's just like a chance, but it still allow you to distinguish between podcasts which will be overly challenging or might be very simplistic, right? And get us something at the balance.
Thank you very much. Again, please.
All right.
Okay, our next presenter will be presenting through Zoom. Oleg Lesota, Stefan Brandy. Let me actually make this larger. Matthias Wenzel, Alessandro Benedetto, I'm really trying, Melchioro, Elizabeth Lex, Navid Rekopsaz, and Marcus Schell. Exploring cross-group discrepancies in calibrated popularity for accuracy of fairness trade-off optimization. Oleg, can you take it away? I'm gonna stop presenting here. You can start presenting.
I'll do my best. Okay. Okay, can you hear me?
Yes, we can hear you. Let me bit. But I'm not sure if, have you started presenting?
Sorry?
Have you started present your slides? We can't see the slides yet.
Not yet. I'm sharing my screen now. I can try again.
Maybe,
wait a second.
yeah, stop and yeah.
I'll share the whole desktop. Is
Yes,
it better?
perfect. Yes, working now.
All right. So thank you very much for the introduction. I'm sorry we are so many authors with so complicated names, but you did a really great job. Thank you very much. So my name is, as said, is Oleg Lesota, and on behalf of my colleagues from Johannes Kepler University Linz and TU Graz, I would like to present you our recent work where we explore cross-group discrepancies in calibrated popularity and also try to exploit them to optimize the trade-off between fairness and accuracy. So in fairness, we're talking here about popularity bias. Probably everyone knows this is a harmful phenomenon occurring in recommender systems, and it basically means that popular items get overexposed at the expense of less popular items. And this phenomenon is harmful in many ways. It's harmful for users, which are not always happy to get only popular content recommended to them. It's harmful to item creators, for new and niche item creators, which do not get enough of deserved exposure. And also content provider platforms are not happy playing only popular content because it is expensive. So we are working on the user side of popularity bias here. One of the ways to somehow estimate, evaluate it is through calibration of item popularity distributions. So what we can do is we take the whole collection of items we have, and we assign a popularity label to each of them. So the item is either low popular, of average popularity, or highly popular, and we can count how many of each type the user have consumed. This creates a popularity distribution as on the left. And the same can be done for the items recommended to this user. And by comparing these two distributions, we can make some judgments. What does our recommender do? So does it recommend more popular items than they should or not? One of the ways to express this numerically is through Jensen-Shannon divergence. This is a bit more general than popularity bias, but it works. So in our case, it's bound to 0-1 interval, and the higher it is, the more miscalibration between these two popularity distributions we have for each user. Building on that, so Himan and Masood in 2021 proposed a very nice post-processing mitigation technique called calibrated popularity, where the idea is for each user personally to take top 100 recommendations and from them combine a list of 10 items which maximizes the following objective. First of all, we want the relevant scores to be as high as possible. This is our evaluation of the utility. But at the same time, we want the miscalibration between popularity distributions of consumed items and recommended items to be as small as possible. And of course, we have this lambda parameter telling us how much weight do we give to each objective. So this is a great approach. It has been shown to work really well with metric factorization methods as well. Our question was, how transferable is this success? How does this trade-off look for other architectures, other recommenders? Do they all show the same picture of the trade-off if we change the parameter lambda? And the second question, actually, do all user groups benefit to the same extent from this mitigation? Maybe some user groups require more, some require less. And if it is this way, maybe we can exploit this and get a softer trade-off for the whole system. Trying to answer these questions, we took two data sets. One is a sample of LFM2B, 100,000 items, and a smaller, less sparse movie lens 1M. We considered 5 algorithms of different architectures. And also we considered 2 user groupings. One is mainstreaminess, where each user is labeled as preferring a lot of popular content, average popular content, and very little of popular content. This is the low pop group, and also gender. So moving to the first research question, how do different algorithms respond to this mitigation? For each algorithm, we conducted this experiment 9 times or 10 for 10 values of lambda from 0 to 0.9. And we plotted these curves. So on x-axis, we have NDCG, our utility metric. On y-axis, we have Jensen-Shannon divergence. This is miscalibration metric. So the more we have here, the worse the calibration is. And we can see that indeed for different algorithms, the patterns are different. For example, the multi-VAE in OMF, as soon as we start mitigation, we get a really notable drop in the utility. And for other methods, like for BPR or like GCN, the descent is more uniform. For item KNN, we can also note that for a small value of lambda, we get a really increase in utility, which is interesting. And moving on to the second research question, analysis of different user groups, how do they respond? Let's concentrate on the mainstreaminess. So in green, we have users who prefer least of popular content, in yellow, the most. And we plotted for every group the same curve. So the top point corresponds to lambda equals to 0, where we do not perform any mitigation at all. And the bottom points correspond to lambda 0.9, where we do as much mitigation as possible. We note that for all algorithms, the green line corresponding to low pop users is actually almost vertical. It means that we can successfully mitigate this miscalibration at the same time without losing much of a utility. And for item KNN, we can even see that this group enjoys as much of mitigations as we can give to them. So they're happy even with the higher values of a lambda. You can also note that for high pop group, made in yellow, I hope you can see it, we have a slope. So they are really not happy at some point with the mitigation, and they would prefer to have more popular items if we consider utility as their preference in DCG. Finally, we decided to try and exploit this. So we thought, what happens if we give a personal lambda value or individual lambda value for every user group? We split our data sets into halves. And on one half, we estimated optimal parameters lambda for every of these 3 user groups. And on the other half, we applied these parameters. So for low pop group, we applied this estimated optimal low pop lambda and so on, and checked the trade-off. So here in red, for both data sets, we see lambda pop is exactly the scenario where for each mainstreaminess group of a user, we give a separate individual value of the lambda. And indeed, if we treat this, the NDCG and Jensen-Shannon divergence one-to-one in terms of importance, we indeed get most beneficial trade-off between fairness and utility. To sum up everything, first of all, the way utility fairness trade-off develops with increase of lambda is very algorithm and user group dependent. In particular, users, from what we have seen, users preferring less popular items, unlike users of other groups, enjoy more beneficial trade-off. So even if we crank the lambda up to 0.9, they're still happy. And finally, selecting group-specific lambdas can lead to an overall more beneficial trade-off for the whole system. And yes, so from this we conclude that we really need to look out when we apply some universal mitigation method to our new system, because the interaction between those can be unexpected. And indeed, we can use certain discrepancies, if the groups are selected right, to our advantage. And with this, I thank you very much for your attention, and I'll be happy to answer your questions. Thank you very much.
Thanks much, Oleg. We'll take questions from in-person attendees.
Thanks very much for the work. I have one question about the kind of differences that you saw for different algorithms, how smooth changing the lambda was behave. Like basically it was a difference between how it behaved, like smoothly or not smoothly for different algorithms. I'm wondering if this is because different algorithms, they might produce a different scale of the kind of relevance scores. So I don't know if you kind of try to kind of calibrate those scores as well to all become the same scale as the Jensen-Shannon divergence?
Yes, so in order for this operation to make sense for different algorithms, thank you for the question, I love it. And that's why I rushed to answer. We indeed, for every algorithm, we scaled the relevance scores to 0-1 interval, so that we have the same interval for relevance and for Jensen-Shannon divergence. So we took care about this. And yes, so this is what we see in the end. Does it answer your question?
Thanks. Yes, perfect. Thank you.
Any other questions from in-person audience?
I would maybe, sorry, add to the last question that this kind of discrepancy gives us idea about the quality of the top 100 recommendations for every algorithm. So if we get a massive drop at the very beginning, it probably means that we get the utility by these algorithms by maybe concentrating maybe highly popular items at the very top. And once we start shuffling, we get a significant drop. And this could be a indicator of the quality of recommended items produced by different algorithms. Yeah, thank you.
Thank you very much. So if you stop presenting, that would... Okay. The next paper is Bias and Feedback Loop in Music Recommendation, Studies on Record Label Impact from Peter Nies, Andres Ferraro, and Moritz Hoppler. Are you Peter? Yes, perfect. This was it, right?
Thank you, Sarah, for the introduction. Can you hear me? Yes. Oh. Welcome to the talk. In the short amount of time, we'll try to bring in, hopefully, a new perspective into music recommender systems. So I'm going to talk about bias and feedback loops in music recommendation, and particularly focused on the aspect of record labels in this context, or did first steps in this regard. So the situation we're dealing with in music recommendation, we have a multiple or a multi-stakeholder situation here. The typical streaming consumption situation would be that you have the item consumers, which would be the listeners typically. We have the item providers. Many people think that these would be the artists, but they can be many other types of item providers as well. So there's a difference whether like this is the composer, the producer, the performer. The right owners are actually the ones that do care a lot about which items are provided. And as proxy or through proxy, also the record labels or the distributors of that. So it's actually a very complex situation where there's many interests in this process of music recommendation. But also the streaming platforms themselves as intermediaries, of course, they are a stakeholder in this process, and they have an interest in this. I have to go closer to the microphone. Thanks for letting me know. So they all have different objectives, these different stakeholders. In this short paper here, we're not going to discuss really the open questions that immediately arise from all these different situations, like what does that mean in terms of diversity and how do we have to change recommendations or calibrate them or anything? What does it mean in terms of visibility for artists or the fairness even? These are all important questions, and that will be basically what we intend to do in future work. But for this, we're going to take the first steps of just assessing what the situation is. So what are the goals of this work? As already mentioned before, we're doing analysis with respect to the particular stakeholder of the record label. And we have a number of steps that we're taking in this paper. So the first one is we actually have to figure out who are the record labels for the music items that we're recommending. So this is an important information, but that is usually not present in the metadata. So we do know who's the artist, who's the what album was it produced on, released on, like which year and so on. But who was actually the distributor and who's the company behind it? Oh, okay.
I apologize for the online audience. Sorry. Can you see my screen now? Can someone on mic? On? Okay, perfect. Sorry for that.
No problem. Let me just briefly skip back so you see what you missed. So that was the introductory slide, right? So just the names and the title. So then we had the situation that I discussed with the different stakeholders and what we're dealing with. And now I'm at this slide here, what we're doing in the work actually. So the first part being retrieving the information or actually accessing this information about the record label. And once we have that information, we're first going to do an analysis of what actually distributions look like in data sets. So really, what is the situation? Because we haven't seen that before. We don't really know what we're dealing with. And then we also do first analyses of the impact on the recommendation process. So we're running some feedback loop experiments to see what do recommenders actually do and how does it impact the distribution of record labels in this through the process. Okay, now I have to. Let's see. I'm just going to go through. Okay, so assigning the record label. So this is a complex task because actually it's a very fragmented area. So the actual distributor or the record label that releases music can be very different in each country. It's usually a small label and so on. But then they're hierarchically organized more or less into one of the three major distributors of music worldwide. So you have like the big three being Universal Music, Warner Music, and Sony Music. And somehow, or most of these small labels are somewhat connected to them and make use of these labels. It's actually a bit more difficult because in different countries, there might be different major distributors for certain labels and so on, but we're not looking into these kind of things. They also might change over time, but we're going to neglect that. And there's also independent labels, of course. Not that everything is released by one of the major labels, but some are just independent. And actually through streaming and so on, it should be easier to get your music distributed worldwide without having a major distributor. Anyway, difficult situation. The low-level record label, as we call it, so basically the first distributor that they're signed with, is something that you can most of the time get through the Spotify API. So this information is actually available in the API, but it's typically some legal type of string where it tells you like what the business is called and so on. That doesn't really tell you to which major label they belong to. And this was the process that we did here. So we started from the Spotify API, and then we used Discogs, which is a community-run website with lots of information about records, releases, and so on, to use this to identify who was the major distributor, and also Wikipedia to get like the connections between these different labels. And we analyzed two data sets, the first one being the Million Playlist data set, which was used in the Spotify RecSys challenge in 2018. So name says it's like a million playlists that have been generated by users, and the other one being the LFM2B set of with Last.fm profiles, and we use the Spotify URI subset, so that has been provided by the colleagues in Linz who presented in the talk before, and we're going to use this one for our analysis as well.
So first of all, the process of how we actually got to this this information, so the different steps, you can see that we started with like trivial mappings of like what is like everything that has Universal or Sony or Warner in the name, where it's kind of obvious. We had to map them. This is what you see at the very, very left on the left graph there. And then through the different steps, like asking Discogs, Wikipedia, and so on, we got more and more information. So starting from like 37% of cases, we eventually ended up with assigning all of them. Everything where we couldn't assign something was just independent ultimately. And we see a huge huge presence of Universal Music in the Spotify data set, followed by Sony and Warner, and then a smaller part is actually independent music. If we look at the other data set, the Last.fm data set, we see that the distribution is quite different. So here we have actually, so that between the major companies, it's comparable, but we have much more independent music with Last.fm than we do have in the Spotify data set, right? And we also start with all the assignments we already had. So it starts with a much higher value already here, but basically we ended up with all the assignments. But this is a very different type of data we're dealing with actually. So when we talk about music recommendation, it's taking a data set, it really makes a difference which data set you're taking because you have very different characteristics there. Okay, next thing, the diversity within the individual user profiles or playlists. So one data set playlist, the other one being listening profiles. And here we use the Simpson index, which is a simple entropy-based method. I don't think there's much to say here, but it's just a choice that we took here. The important thing is that we get this value of lambda, which is the Simpson index, and if it's a low value of lambda, we have a high diversity of record labels in our playlist, and if it's a high value of lambda, we have a low diversity in our playlist or profiles. And so we plotted the playlist or the profiles according to the lambda values and to the histogram of how often these lambda values appear in the data set, and this also again looks very different between the two types of data sets that we have. So on the left, we see the Spotify million playlist data set, where we have like a lot of playlists, of course, with a lot of diversity is what you would expect. People don't really care what the record label is. They would just listen to the kind of music they like. And so they're basically all over the place, all different types of record labels. But then we have this curious peak at the very end. So there's a lot of playlists that actually have no diversity in terms of record label when it comes to this analysis. We still haven't figured out what exactly they are. We dived a bit more into the details here. A lot of it is soundtracks, actually. It's all from the same record label, different artists and so on. So if you have playlists like this, you get this like lack of diversity that way, but still it's a lot actually. So that's going to be an interesting investigation in future work. So for the Last.fm data set, we don't see that. It's actually very different shape, and the no diversity playlists are basically playing no role in this context here. Okay. Moving on, if we look further with the ones, particularly on the right side in both of these graphs, so the ones where we have a high Simpson index, so no diversity, we're interested in that. We also see that with the Spotify data set, we actually have a high presence of Universal already in the overall distribution. But if we go further to the right, this presence of Universal increases even more. So the less diverse the playlists get, the more Universal becomes present in these playlists. So there's definitely like a lot of Universal dominated playlists in this data set. On the other side, we also see this like rich get rich effect on the Last.fm data set. So maybe it's just a matter of this, like where this bias is coming from. Here we start with a lot of independent music already, and the further we go into less diversity, it's getting more independent, but it's in absolute numbers, it's much less here, but still we see the same effect here. Gonna speed up, I'm sure. So next thing, we ran our simulation experiments. How did we set up the experiment? We used one algorithm only. We were only interested in seeing if there's any effect. So we used matrix factorization recommendation algorithm using the ALS implementation. And our assumption, which is a strong assumption, granted, is that from each item that's from the list of recommended items, the top 10 are actually considered relevant. So let's say the user in every iteration of the recommendation algorithm says, oh, the top 10 are really relevant for me. I'm going to consume these. And they go into the user profile. And then we do another round of recommendations with the updated user profile and see what the recommendations look like. And so this we iterate a couple times, and then we see what happens in terms of the distribution of the record labels. So that's what we're doing here. And we have two metrics to look into. One is the average position of the first occurrence of a record label, and the other one is the overall distribution, which is the recommended one, overall the iteration, in the all the playlists or profiles. So for the million playlist data set, due to limited resources, we could only run the experiments with a 1% sample. So actually our results are not very conclusive. That's not the whole data set yet. But what we see here is that this is quite stable. So over all these iterations, we actually keep the same the distribution of record labels in the recommendations. So there's not much to see here. But again, it's a very small sample, so there's more work needed on that side. If we look at the Last.fm data set, it's actually interesting to see that things change over time. Okay, so what we see is that we have a lot of independent due to the distribution and so on. It's very important. But particularly if you look on the right side, like the overall recommended approach over the first few iterations already, the number of tracks by independent artists actually in the recommendations goes down and is taken over by Universal Music. So they were not the first place, but they turned to be a first place. And we also see like a change here. So Warner Records also goes up and Sony Music also goes down over time. Then it stabilizes at some point. Okay, I'm coming to the conclusions. So this were just some first insights. We did see, however, that different data sets exhibit very different distributions, different characteristics when it comes to this particular view of record labels in here. And we think that's definitely worthwhile to be explored further. First of all, in order to improve recommendations, but also to see what are the data sets actually doing that we're having and what are we really simulating here, and which particular use cases are contained in those data sets. So it's not just, as I said before, listening history and we throw in an algorithm and then we'll see what happens, but it makes a huge difference which data set we're using. We've seen that with the feedback loop simulations that it's quite stable on the million playlist data set, but again, this is non-conclusive from our perspective. And we do have this trend of promoting Universal and Warner in the Last.fm data set at the expense of independent music and Sony. So what are our next steps? Of course, we want to see, does this information actually help us in making recommendations better, or how can we bring this into the process, or maybe make recommendations more fair and so on. And that immediately gets us to this next question, which is a longer term perspective, but a discussion. So we didn't have that discussion, or we really can't give the answer here, but what music recommender should actually aim for? So what the objective should be? Should it be diversity, coverage, visibility, fairness? And for whom particularly, for which type of stakeholder, is a discussion that we should have, because this really defines on what we're going to do and which information we need in order to do that. Thanks very much for your attention.
Thank you very much, Peter. Very interesting talk. Questions from the audience here? From online.
Okay. I have a question I can ask myself.
I actually have questions. This is really interesting. Did you look into popularity and, for example, how there are two things come to my mind. One is markets, for example, where these data are coming from. For example, some are more dominated in specific markets and some are not. And the other one, like, for example, I think one thing that was really interesting was the playlist one, that the Universal was for playlists that was dominated in some playlists, right?
Right.
So I'm really curious, what is it? Right? I'm sure you are too, but is it like popularity, one of the things that come to my mind?
So in the million playlist data set, for sure, is popularity to a large extent. So I think what was done, when you asked the colleagues at Spotify how the set was created, but I think it was a representative set in terms of popularity, particularly. And the side effect or the effects that you see might be an effect of that, because Universal just has the most popular artists. So if you make sure that this is a somewhat realistic data set in terms of the playlist, you do have that dominance. And I think also with regard to the challenge, maybe the goal was also to have more popular artists, because it allows to
share information,
extend to that creative task. That was also part of the challenge, where you can add additional sources. If you don't have popular artists, you have cold start problems in terms of metadata and so on. So maybe that's not working so well there. Maybe that was also a reason behind this. So again, it's a question to be posed as well to the
it's interesting. I think the other aspect that maybe I will add is there's a direct deal relationship with these as well. So other than if we should optimize for diversity, coverage, visibility, fairness of these, there's also that aspect of cost that matters, the multi-stakeholder aspect.
So I mean, as you mentioned before, if industry wants to give us some insights on that, I think
definitely.
we would
I'll encourage them.
Oh,
Yes.
Thanks for the talk. I was wondering, is it open, the data sets the gathering you've done?
Yeah, I think it's not online yet because we still have to figure out where the right place is to do it, like the amount of data we have to, but we will share the data. So the link is in the paper.
And you have also other labels than just these three?
So for this study, we looked at the three majors, but what we're gonna do is we're gonna include the original low-level information that we got from Spotify. So what the actual label was and the copyright information. That makes the data set actually much bigger than just like the index of the major, like including that plus the assignment that we ended up with.
Okay, great. Yeah, I'd love to.
Yeah, and also the code is available. So in theory, that's the whole point of like for all data sets that we have in that area of getting like this additional view and the record labels on top of that. Yeah.
Thanks.
You had a question?
Really, I have time for my own question. So the question is like, I would think the question would be like, how does it work? Does it actually improve recommendations? Because we also did one tiny first experiment in this direction. Because with the mail and playlist data set, we can rerun the simulate or like the challenge on crowd AI at this point. And we took the approach from Dietmar Janach's group from 2018. And just use the record label information for calibration on the record label and re-rank that. And for a couple of these playlists, I think it's like 7 years so on where this makes a difference. We got this tiny increase. So we could actually, beat the original approach in the ranking based on this information just because we could optimize for this type of information. That doesn't make the recommendation any better, but it would in a challenge allow to jump one place or something.
Definitely.
And I mean, I think that's still relevant from that perspective because
and the multi-objective part, I think there's a lot of work that could be done on this data set as well. Yeah, thank you very much again. Please give it up to Pete and his colleagues. Our last but definitely not least talk of this session, how neighborhood exploration influences novelty and diversity in graph collaborative filtering. I'm gonna try to read the author list. Vito Walter Anelli, Yashar Delju, Tommaso Di Noia, Eugenio Di Sciascio, Antonio Ferrara, Daniel Malitesla, and Claudio Pomo. Please, we have Vito here, right? Daniel, okay. Let me bring this up. Please.
Okay, thank you very much for the introduction and for the effort in pronouncing some difficult names, I can imagine. My name is Daniele Malitesta, and I'm a second year PhD student at Politecnico di Bari. I would like to thank the other authors of this work, of course. Okay, let's get started. So graph collaborative filtering is gaining more and more importance in the literature. And this is due mainly to the fact that it builds on graph convolution networks and their layers. And graph convolution networks works by aggregating the information from the neighbor nodes into the ego nodes. And the iteration and the process is repeated several times for several ops, and thus and this process is known as message passing, and thus the collaborative signal is actually and effectively distilled throughout the whole graph. Okay. We can distinguish between two classes and two families of graph collaborative filtering models based on the message passing. So we discover both the explicit message passing models that are able to actually build and write a formula for message passing, while the implicit message passing models try to use some mathematical tricks to overcome some issues known in the literature for graph collaborative filtering, and so they do not use explicit message passing. All these models have shown to provide very accurate recommendation values and measures, but as we know, and we are here for these mainly, there are several interests in both users and business point of view to have multiple and other objectives to be just optimized all at once. And so we have discovered that all these graph-based models cannot fulfill all these multi-objective measures and metrics, or the ones that do are not studying what is the influence of neighbor exploration on the use on the accuracy, novelty, diversity trade-off, for example. So our contribution is to study the impact of different kind of neighbor exploration, so explicit and implicit message passing on the trade-off between accuracy, novelty, and also diversity for 6 state-of-the-art models from graph collaborative filtering, and then with a simple mathematical trick, we provide a simple reformulation of the message passing, which considers both same and different type node exploration, and we try to understand what is the impact of this kind of node exploration for this trade-off. So for this very simple mathematical reformulation, we first need to give some useful notations. So we introduce the user and then item node embeddings, then the function to produce the aggregation of the messages, and finally the set of neighbor nodes for each ego node. Then we can provide the formulas for 1, 2, and 3 ops of the message passing. They are quite trivial and they are quite well explored and studied in the literature. So we will not go into this more in detail. But we will go through the mathematical reformulation of the message passing for 2 and 3 ops, because with the adoption of equation 1 and equation 2, we can then rewrite the message passing for 2 and 3 ops. And what emerges is that for an even and an odd number of explored ops, we actually have the node connections for same and different types. And this is also evident from the figure on the right side of the slide. So that's our simple reformulation. For the experimental setting, we used 3 popular datasets from the literature. So MovieLens and Amazon Digital Music and Opinions for the last one. We, of course, did some pre-process stage and phase to just avoid some cold start situations, since it is out of scope. It is out of scope for this paper and this work. Then we considered 6 baselines from the state of the art. So 4 for the explicit message passing and 2 for the implicit message passing. Here are some references to the papers and the complete name for each of these models. So then you can just check on them. And finally, then for the evaluation metrics, we adopted 6 popular measures for accuracy, the novelty, and also the diversity. For the novelty and the diversity, we took into account EPC and EFD. And then for the diversity, we take into account some concentration-based indices, like for example, Gini index and Shannon entropy. Okay, for the result, we will just take into account the Amazon Digital Music data for the sake of brevity of this talk. Okay, from an overall point of view, we can see that while the accuracy novelty trade-off is not dependent on the way we propagate messages, so explicitly or implicitly, we can instead see that for the accuracy and diversity trade-off, the explicit message passing formulation can lead to better measures and values with a limited accuracy drops in the performance. While if we go into a finer evaluation, we can discover that the explicit message passing can lead to more accurate and diverse trade-offs than the implicit one. So it's a confirmation of the first research question. And then we can also notice that the same type node exploration can lead to improved accuracy novelty and accuracy diversity trade-offs. So that's our main observation for the second second research question. Okay, to conclude, we want to and plan to for future extensions to study also models from graph collaborative filtering that explicitly optimize these trade-offs that we have seen in this presentation and in the work. And we also willing to understand whether the same type node exploration can lead to better performance, since we already observed this in the literature and in the experiments. Thank you very much.
Thanks so much, Daniel. Questions from in-person audience? I have a question. Do you think it's relevant to look into add measures like baselines from non-graph based recommendations as well, and in general how they do in terms of this trade-off?
Yes, I think so. Also because we have seen from other papers and works that non-graph based models can lead to better performance, for example, in terms of accuracy. So yes, it would be definitely important to look at them and try to understand if they perform better on the trade-off, for example. Yes.
I see. Thank you very much. Please give it up again. Okay, with that, we are concluding this session. On behalf of all organizers, we would like to really thank all the authors, as well as chairs, as well as reviewers, who really contributed for this workshop to be so great. I really enjoyed it. I hope you guys all have enjoyed as much as I did. You want to add anything, Himan?
Yeah, I also want to thank everyone for being here, and also special thanks for some of the organizers that they couldn't make it in person. My colleagues Mehdi, Masoud, Babak, and Shaghair, they couldn't make it in person. So I would like to thank them again, and thanks everyone again for attending the workshop. It was a great success. We had great papers and discussions. Hopefully we can organize this again in the future. And now we have officially a poster session. So please, if you, do you have a question there? Oh yeah, so yes. Yes, so these are the list of posters, basically papers that were accepted as poster presentations for MORS. They are in the kind of a, in that area. So please check the posters and hope that you will have interesting discussions with the authors as well.
I would like to also thank our online audience for their patience. We had a few small hiccups. We really appreciate your patience. Our authors kindly agreed to provide videos, YouTube videos. We will be linking them to the website, even for posters. We have videos for the online attendees. If you can't see the posters here, don't worry about it. Hopefully you can catch up on the videos as well. So thanks everyone, and hope to see you all soon again.
Thank you, everyone.